we shall try to find the area enclosed by this cardioid given by r equals 2 into 1 minus cos theta. We can absolutely find it out without drawing the cardioid or without understanding the shape of the cardioid by a simple double integral in polar coordinates. But I'm making this video with the aim of showing how without using the computer we can at least guess what type of shape the cardioid or such complicated graphs will be. So I am going to draw this shape first and just magnify it to twice its size to get the initial cardioid. Okay, so here are my coordinates. R equal to 1 gives me this circle, this unit circle. So I want to subtract cos theta for each value of theta from the unit circle in a way. So let's say when theta is 0, then cos theta is 1. So here r equals 1. So the whole 1 is getting subtracted from this. So this point here, that is coming here. Okay. From here, that is from r equals from theta 0. At this point, theta is pi by 2. Where cos theta is 0. So we are subtracting nothing. So this is getting stretched here. Well, here it is remaining intact. Let's see somewhere in between this point where theta is pi by 4. Cos theta is 1 by root 2. I think that's close to 0.7 something. I mean, this might not be the actual rounding off, but it's something close to that. So 1 minus 0.7 gives me 0.3. Right. So where this r distance here is 1. This is becoming something like this. So this point here is getting stretched, dragged to this point. Let's see what is cos. This is pi by 4. So let's say three pi by 8. That is close to 0.4. So if this is 3 pi by 8 here, then this point Here this distance is r equals 1, so it is getting dragged somewhere here at point 6. So you see, we are now getting somewhat of a shape. Like this. And you know that cos minus theta is cos theta. So in the negative also we are getting something like this. Now see, something similar will act here, like at this point this distance is 1. So this will again get stretched by 1, dragged to 1 distance in the negative. This distance is 0.7. So somewhere here this will also get dragged to some 0.7 distance here. I mean, if we try to deduce what will happen to this side of the circle from this, otherwise you can also take a few angles in between and calculate the cost for them. Sorry, I think I did this wrong. Sorry. Okay. If I take pi by 4 here, I mean this is pi by 2 plus pi by 4. Then here it is getting dragged to this side by 0.7. So this will get increased by 0.7. At 3 pi by 8, it will get increased by 0.4. Right? So this shape it will go like this. But I mean, I am using these values here. You can also take some angles like this and calculate their, let's say this is pi by 2 plus pi by 4. You can calculate the cosine and I mean r minus that value you can put here. So the shape is becoming something like this. This is called a cardioid because this resembles a heart. So some medical term. And when I want 2 times 1 minus cos theta, like 0 remains 0. Otherwise, everything gets magnified. And this is not twice. It will be larger. It gets magnified. So that's how you draw a cardioid. Now this has got nothing to do with solving the double integral. we are trying to find the area enclosed by this curve. So the range of theta goes from 0 to 2 pi, and r goes from, like, let's say I don't know what the shape is. So anyway, this boundary is given by this r distance is, if this is r, 2 into 1 minus cos theta. Now I know that this is a nice shape, but even if I didn't know the shape, I could have calculated like this. Like, if this distance is r goes from 0 to 2 into 1 minus cos theta. We are just calculating the area, so it is 1 and r dr d theta. Now r dr d theta comes from the Jacobian of transferring to polar coordinates, like dx dy. I discussed this in class today. X equals r cos theta and y equals r sin theta. So this is cos theta minus r sin theta, r cos theta, dr d theta. So from there this follows, r dr d theta. So we can just evaluate this. I think you can do this. That's all about it. I just make this video so that it gives you an idea of how to draw a shape, if it is a shape that you haven't come across already. What would be a feasible manual technique of drawing an unknown shape from an equation, from a polar equation?